Hello, everyone. Hope you had a restful weekend, and I'm sorry to have to resort to doing this. I had neglected to remember that I had agreed to teach in another class for a colleague, and had also neglected to remember that it was at the same time as my own class. I felt badly, you know, pulling out of that at the last minute, especially since I had forgotten to do it. So I'm going to press on and do that. And I'm just going to resort to recording this lecture ahead of time. And I think it'll work out okay anyway. So hopefully you'll have some grace for me in doing that. Now, one added benefit to this is for your sake, I guess, is that it's going to change the exam plan a little bit. I think that what I'm going to do is give you the exam as a take-home that I will give to you on Wednesday, and it will be due back on Friday. And it will deal exclusively with integration tactics. You do have one more integration assignment, namely on the last section pertaining to spherical and cylindrical coordinates that you should be well into at this point, I hope. And we'll spend some time talking about that on Wednesday if you have additional questions, and we'll review a little bit. But we'll also build upon the information that I'll present in this lecture as well. So hopefully that makes sense. I'll entertain any questions that you have about that on Wednesday. And besides, actually, the take-home idea makes sense because I have a number of students that are actually in quarantine right now. There's a growing number of quarantines happening. So that seems to solve several problems all at once. So it'll all be okay. I think that's all the information that I have for now. Just make sure that you work on the last section of WebAssign and come with any questions on that on Wednesday. Hopefully that's going well for you. What we're about to do is transition into the last chapter of the entire book, and that actually has to do with something called vector analysis. And it's really going to be a culmination of everything that we've been doing in the entire book so far. We're going to draw on everything that we've done, especially some of the tools that we learned about vectors at the end of Calc 2. We've already been utilizing a lot of that in Calc 3, but now we're going to kind of merge everything together and just watch how much we can actually do. And a lot of what we're going to be doing has to do with physical applications, things that that we want to know about. Things like, okay, if I have a fluid flow, how does it rotate around a point? If I just think about that one point, or if I look at a point in some kind of fluid flow, what is happening there? Is material tending to be lost or gained at that point? And those are questions that we can now ask and answer with a fair amount of rigor, given the tools that we've developed over time. So let's get to it. Right. I'm showing you my hand here. These are my notes that I utilize for lectures and whatnot. Figured I would just put these up here and talk through them for the most part. And essentially, I will show you later on that there's some really nice online resources about this material that I think you should take advantage of as we go through chapter 15. There's just some beautiful mathematics going on here in chapter 15, and I don't want to blow through it too quickly without you realizing everything that's going on. So first of all, in this first line right here, we see that in Calc 1 and Calc 2, we studied functions of a single variable, okay? And the way we notate that is like f colon real numbers to real numbers. So these first things are inputs, and these things right here are where the outputs live, okay? So this is f maps or takes inputs from the real numbers to outputs in the real numbers. Okay, we studied functions of that sort in Calc 1 and 2. And at some point in Calc 2, we actually studied these things called vector valued functions. Vector valued functions. And we use that when we were parametrizing curves and things like that. We were saying, well, this circle really isn't a function, but I can turn it into one by sort of changing what I think about as my input and output. So my input is some kind of parameter, a real number. My output was an ordered pair of real numbers on the circle. And we were able to turn something that wasn't a function into one. And in some sense, we thought of those outputs, even though they were ordered pairs, we thought of them as vectors. Okay? That's why we call them vector valued functions. Okay, and they were position vectors, even though they were points, they were position vectors with, tail at the origin and head out at the point itself. Okay, so if we were looking at a circle centered at the origin, then the parameter value that we were plugging in would give us an ordered pair point on the circle. And we thought of that as kind of a position vector from the origin to that point on the circle. And we were even able to do things like take derivatives as that point went around on the circle. And we got those velocity vectors and acceleration vectors as we did so. Now in Calc 3, we've shifted our focus back to something that we're more used to, things that have real number outputs. So here we had real number input and ordered pair, ordered triple outputs, vector valued functions. Here we have, pair of real number inputs and then real number outputs for the most part. And sometimes in Calc 3, we've been looking at ordered triple inputs and real number outputs. Okay. Well, what we're going to do now is we're going to kind of mix and match some of the things that we've been doing before. Okay. So we start with a couple of positive integers. That's what this means. Okay. Don't freak out about the notation. NM, this guy right here just means belongs to. Okay. You probably have seen that before, but belongs to Z plus is just the positive integers. It's going to be a function from the ordered n tuples of real numbers to ordered m tuples of real numbers. Most of the time, it's just going to be like ordered pairs of real numbers to ordered pairs of real numbers. Okay, if these numbers are, are not the same, that's okay. We'll still call this a vector field, but for our purposes, most of the time, we're going to have n and m be 2 or 3. So that means we're going to have ordered pair inputs and ordered pair outputs, or ordered triple inputs and ordered triple outputs. Okay. So, and by the way, this is really just a generalization of what we've been doing all along. We're just kind of amping up the generalization. And by the way, if you go from ordered pairs of inputs to ordered pairs of outputs, that means you need 2 dimensions for the input and 2 dimensions for the output, which means that the graph is going to live in 4-dimensional space, which we cannot visualize. So the way that we are going to be able to visualize these things, even though we can't visualize the graph, is we're going to be able to visualize them using vectors, where the first ordered pair input is going to be just that point. The input is going to be that point in 2-dimensional space. And the output ordered pair, that's going to be the head of that vector in 2-dimensional space. And you just draw an arrow from the input to the output. And that's why it's called a vector field. The function itself can be visualized by vectors. Okay. So generally speaking, we use like M. Okay. So like, look, we have a real ordered pair input. And then we have a function of 2 variables, m of xy, and another function of 2 variables, n of xy. And these are the so-called x and y coordinate functions. Okay. And so the input is an ordered pair and the output is an ordered pair. And we think of this thing as a vector with its tail at the original ordered pair, or with its tail at the original ordered pair, x comma y. And then we draw m of xy, n of xy emanating from that point so that we can imagine what's happening here. Typically we use m and n to notate the X and Y coordinates of these vector valued functions. Then we use P for the third one if we happen to be dealing with a vector field in three-dimensional space, okay? So we would call this a vector, we would call the two-dimensional situation a vector field in 2D, and in the three-dimensional situation, a vector field in 3D, okay? So once again, and by the way, a vector field from three-dimensional space to three-dimensional space, good grief, that, my friends, is going to require 6 dimensions to fully visualize the graph. We can't do that at all. So again, to give us some idea of what's happening, we take sort of the three-dimensional input, x, y, z, use that as kind of the anchor point for a vector that is determined by the three-dimensional output, m of x, y, z, n of x, y, z, p of x, y, z. And we just draw that vector emanating from the input point x, y, z. So you have input point x, y, z, output point m, n, p, all of which depend on x, y, and z. Okay? Okay, so why are we talking about this? Well, because this is a good way to model sort of velocity fields. I have this funny little thing here, you know, whenever you see people kind of coming out of chapel and running to class, you see people running around the lake in various directions, you know, or running up sidewalks or kind of going over to the BTS or the ENS or the student center or what have you. And you kind of see these little particles. If I were hovering above the campus as like a drone watching what's happening, you would see this kind of flow going around, okay? You can almost imagine like each person sort of giving a vector that's showing their instantaneous direction. And that would be an example of a vector field. And in that sense, if I was hovering above and looking down, it'd be like a two-dimensional vector field. Okay, a fluid flow, you can either think of those as kind of on a surface itself so that it's two-dimensional, or you can think of it as three-dimensional. And wind, which really is kind of a type of a fluid flow as well, probably see that sort of thing on the news. You know, they'll show a map, like a topographical map on the news, and they'll say, look, the wind's blowing in this direction, and they'll kind of draw an arrow, and they'll draw the arrow longer if the, you know, magnitude of the wind velocity at a given location is larger. And they'll kind of say what it is. They'll say, oh, it's 20 miles per hour, you know, to the north by west or something. Okay. And what I'm going to do is now I'm going to go over, and by the way, I have a couple of examples here of the sorts of things that we might be interested in looking at. Force fields. This is the famous gravitational field. Okay, X, Y, Z is a point in three-dimensional space. G here is a gravitational constant. M1 and M2 are the masses of two bodies in space. Okay, and R is the distance between those two bodies. Okay, and then this is just a scaled unit vector that you know, that represents that distance between those two bodies. Okay, this is a pretty famous formula that you know, is related to Newton's law of gravitation, or the one that he proved. It wouldn't have looked exactly like this when he proved it. This is kind of the vector rendition of it, but it has to do with kind of the force being inversely proportional to the distance between the two bodies, gravitational force being inversely proportional to the mass, or to the distance between the two bodies. Okay, so that's kind of a natural rendering of where you might see this show up. Same thing with electronic force fields. You have a similar formula show up. Okay, and I'll come back to this a little bit later, but we've actually played with these vector fields before, believe it or not. We've seen the gradient. Yes, and the gradient is itself a vector field. If you think about it, it takes three dimensions of input, three variable input, and it has three dimensions of output: the x derivative, y derivative, and z derivative. Right? And we've already seen just how useful the gradient actually is. Okay, so that's probably one of the most important reasons that we're looking at this, is kind of the fact that we saw how useful the gradient is, and that it's a vector field, and that ought to motivate us to learn more about vector fields. Okay, so what I want to do now before we move on in these notes, I want to go over here. This is a fantastic resource. Okay, I'm always trying to look for sort of online resources that you would have access to even after your time at Cedarville. Mathinsight.org. It's a very good website, very good math website. Now, not all math websites are created equal, and this one certainly does stand out. They just have some fantastic little threads, learning threads that you can go through. You can look up lots of different topics. If you're ever in a math class and you're like, man, I don't know what's going on right now, you can always go to Math Insight and actually glean a lot from it. Okay, find a thread and just kind of click through. Lots of times they'll have next and previous and recommended things that you can go to. I just want to go through this with you. So this is like the vector field overview that they have. Again, a vector valued function f, capital F, and notice they use this bold-face F. Now typically I'll write F with an arrow over it just because I'm not capable of writing F with bold-face type, okay? So F mapping two-dimensional input to two-dimensional output can be visualized as a vector field. At a point xy, we can plot the value of capital F of xy as a vector, like I said, with tail anchored at xy, such as in the following figure. And here's the picture that they do. So here's the input xy, and then whatever f of xy is, they draw it as a vector. They draw it as a vector emanating from x comma y. Okay. So and what you do to get an idea of what the entire vector field is doing, rather than just at a single point, is you plot this at various points. And there are lots of resources online that you could go check out on your own and actually graph certain vector fields that are given to you. Okay. Now I will say that on this website, you know, they use just regular old parentheses here. That's fine. That's fine. But you know, sometimes just to emphasize the fact that you think of this thing as a vector output, you can put angled brackets around that, or you can write this as yi plus, or I guess in this case it would be minus, okay, yi minus xj, okay, and that would be your vector field, okay. So, and you would draw these vectors emanating from the input point x comma y, okay. So let's kind of do that for a few of these. I do this here. So f of 1, 0, if you plug in 1, 0, right, this vector field, it says to swap x and y and negate the x coordinate. Swap x and y and negate the x coordinate as you do that. Okay, so f of 1, 0, you swap and negate the 1, so you get 0, negative 1. So don't you see, if I plot the point 1, 0, okay, so it says plot the point 1, 0, plot it from right here. I should draw the vector 0, minus 1 emanating from that point, which is what they have done here, right? So they've done that right there. Okay, they've used a green vector right there. They do that for several others. F of 0, 1, you flip x and y and negate the x coordinate as you do that, but in this case it just remains 0. So f of 0, 1 is this, and they've drawn the vector 1, 0 emanating from that point. Okay, f of 1, 1, which is this. Okay, f of 1, 1, you flip and negate the x coordinate as you do it. So it's 1 minus 1, which is this vector right here. Okay. F of 1, 2 is 2, negative 1. And they've drawn that as a vector emanating from the point 1, 2. Okay, there it is. And you start to get an idea, you're like, huh, that's interesting. That's sort of starting to take shape here. I wonder what would happen if I would just keep drawing these vectors everywhere. Well, turns out that you can get kind of unwieldy if you obviously try to draw a vector at any point. So what you typically do is you pick out sort of a, a sampling of vectors around, in the XY plane, if you have a vector field in two-dimensional space, and you just try to get a feel for what's happening by sketching several of them. And a lot of times you'll even scale the vectors back. You still want to keep the relative lengths the same, but they say they in this next picture, they've drawn the vectors at about 40% of their original lengths, just so that you can see several of them. And then you get a picture that looks kind of like this, okay? Get a picture that looks kind of like this. So this little two-dimensional vector field. Now the vectors themselves have been reduced in length by 40%, but no big deal. You still get the general feel for what this thing is doing if you were thinking of it as kind of like a fluid flow. And the relative lengths are preserved. So you know that, the fluid is flowing faster, right? If you have the velocity of the vectors represented by these, by the lengths of these vectors. Fluid is still flowing faster at the bigger length vectors, okay? And they give another example. So that up there was this right here was the vector field f of xy equal to y comma minus x. And you get something that looks like this. Notice it's kind of, it feels like it's kind of swirling around like that. Yeah, that's interesting. And that's a phenomena that we'll talk about here in just a minute, a little bit more. Okay. Here's another one, f of xy equal to x comma y. Okay, x comma y. And that, they say, looks like an explosion emanating from the origin, which is absolutely true. I mean, look at this. They sort of draw this thing, and it looks like, obviously, the further you get away from the origin, the bigger this thing is, because x comma y as a point is going to get, bigger, right? Which means the magnitude is bigger. So yeah, it does look like an explosion emanating from the origin. So here it looks like almost like stuff is kind of exploding out of the origin, or is almost, being created at the origin, okay? And it turns out that that's another phenomena that we're going to want to study pretty soon. Like, how can I tell if at some point in a vector field, whether or not there's more material flowing out than flowing in to a given point on, overall? And that's something we'll be interested in. If indeed there's more material flowing out than flowing in, that's going to be called a source. That point will be called a source in the vector field. And if less material is flowing out than was flowing in, it's like you have a leak right there in the vector field. And you call that a sink, okay? And up here, like I said, you were noticing some swirling tendencies right here, some swirling tendencies in the vector field. We're going to want to get a handle on that. That's going to involve something called the curl. Curl has to do with trying to feel what's going on with the vector field at certain points in terms of swirling tendencies. That's going to be curl. We'll talk about that really soon. Okay. Down here, this creation of material that is, it looks like more like, if I were to focus on this point right here, it looks like, look, the vectors are kind of bigger on this side of it than they were kind of coming into it, right? So the vectors are smaller here and bigger over here. So this point right here would be like, right, this point right here would be called a source, okay? Seems like creation of fluid or expansion of the fluid is happening there. Expansion is happening there, okay? But it's also possible to have contraction of the fluid there, which you would call it a sink, okay? And there's going to be something called the divergence of a vector field. It's going to tell us about that. That will measure whether or not certain points happen to be sources or sinks in the vector field, okay? But you can have vector fields in three-dimensional space. Here's one, f of xy is equal to xyz. Again, it will look like a big explosion out of the origin. Here you can actually play around with these things. Pretty cool. You kind of look at what's happening here, right, from different directions. Pretty easy to get mesmerized by some of that, okay? There's a three-dimensional vector field right there. And again, you still might be interested in kind of these swirling tendencies, so like curl, and this this expansion and contraction tendencies, which is the so-called divergence, a divergence of a vector field. And we'll talk more about that real soon, more rigorously than just us talking out loud to each other. So look at this thing right here. Here they're trying to get us to think about, so up here, we have this explosion, so there seems to be expansion of the fluid at given points, okay, in this vector field. So there we might, we're saying something about divergence of the field, okay. Down here, it looks like, if I play around with this a little bit, there's definitely some swirling going on here. Yeah, so like if I look down right there, looks like there's some swirling going on. It's kind of interesting. It looks like it's kind of going, okay. There's some swirling like that going on, yeah. And I should be careful. It's not really, curl is not measuring swirling tendencies on a large macroscopic level, but swirling tendencies at a point, they very like infinitesimally small point, okay? So it's microscopic tendencies, not macroscopic tendencies. Same with the divergence or the contraction or expansion of fluids, okay? And there's some more examples here. This one's probably, a little bit more muddled what's happening. Okay, but you can see this fluid kind of flowing around in here. And again, I hope it's clear how these things are being generated. You just have X, Y, Z input, and then, the output is a vector that you plot from the given input point. Okay, so let's talk about this notion of divergence of a vector field. Okay, so what is divergence? Okay, well, the divergence and the curl, okay, are vector operators whose properties are revealed by viewing a vector field as the flow of a fluid or gas, as we've been kind of talking about. Okay, divergence of a field is pretty easy to understand intuitively, as we've already talked about. This looks like the fluid is kind of exploding outward from the origin. And that notion is captured by the divergence. And here's how you notate this thing. div of f, okay? Divergence of the vector field f. And the divergence is positive if the flow is expanding at a given point. Okay? At a given point. This is all focused on given points in the vector field itself. The divergence of f is positive if it's expanding at a given point. Okay? And then it says, by contrast, the below vector field represents the fluid flowing so that it compresses as it moves toward the origin. So like if I were to concentrate on this point right here, you see that the vectors coming into this point are bigger than the vectors that flow out of this point. And therefore, this thing would be called a sink, which means that fluid is being compressed there at that point, okay? Fluid is being compressed there as opposed to expanded, okay? Okay. All right. So divergence at this point would be negative, negative. In fact, at almost every point in this vector field, it looks like the divergence would actually be negative. Negative means that you have net loss, or you have compression of the fluid at any given point. Every point is a sink, okay? And if the divergence is positive, that's telling you that material is being created, the fluid is being expanded at a given point, and so you have a bunch of sources in that case, right? And we're being sort of vague on purpose right now. And the same thing here. Here's a little picture of a three-dimensional situation, which you could amuse yourself by, playing around with some of those. So it's a great little website, I'm telling you. I've messed around with it quite a bit. Essentially, I said that all of this is happening at a point. They try to help you visualize that by thinking about a sphere, okay? You can actually move this sphere around and thinking about whether overall the vector field is tending to come out of that sphere or go into that sphere. Okay, that is that sphere acting as a source or a sink? Is it tending to rob material or create material? Okay, and essentially this sphere idea is just in a larger scale notion of us just trying to understand what's happening point wise, but it really is point wise. That's what you're concerned with divergence. Okay. Later on, we'll look at something called the divergence theorem. And the divergence of a vector field and the flow out of the spheres are really are closely related to each other. But again, it's understanding this at a point that really does end up being the important matter at hand. Okay. So I want to sort of, instead of us just talking vaguely about things, I want to give you formulas for the divergence and curl, and here they are. Okay. So the divergence of a vector field, and look, we're going to give the divergence and curl of a vector field in three-dimensional space. And by the way, I mean, even if you can always turn a vector field in two-dimensional space into one in three-dimensional space by merely appending a 0 z coordinate to both the input and the output. Okay, so you could just append a 0 coordinate to the input and the output. I hope that makes sense. Okay, so the third component function for the vector field would just be the 0 function. So for instance, if I were right here, they're using F1, F2, and F3 as the component functions. Of course, if I take the y derivative of if I take the y derivative of the third component function, it's going to be 0 because the third component function is the 0 function. Okay, and likewise, if I take the if I'm working with a vector field in two-dimensional space, if I take the partial with respect to z, I'm going to get 0 because we're not moving in the z direction at all, right? Z isn't actually going to be appearing anywhere in those functions, just going to be x and y. Okay, so a lot of this stuff goes away when you're dealing with vectors in two-dimensional space. Okay, but the divergence of f is given by the partial of the first function, right? So our vector field f is given by f1, f2, f3. Okay, and by the way, I mean, we used MNP in my notes a couple of minutes ago, but that's okay. So you take the x derivative of the first thing, the y derivative of the second thing, and the z derivative of the third thing. What's really happening here, I'll explain the divergence one. We'll take a closer look at the curl situation a little bit later and try to explain where that crazy formula comes from. Good grief. And how in the world do you remember it? We'll talk about that in just a minute, though. The divergence one, you essentially just want to measure, okay, how much change is taking place in the first coordinate? Like, am I tending to gain material in the x direction or not? And it turns out that's precisely measured by taking the x derivative of the first coordinate. And then you say, am I tending to gain or lose material in the second coordinate? Well, it turns out that's precisely measured by taking the y partial derivative of the second coordinate of the vector field. And similarly for the third coordinate, you just add up those x, y, and z gain or loss of fluid, and that's going to tell you what's happening at a given point. So you add up those rates of change, and that's going to tell you what's happening at a given point. Am I tending to gain or lose material at a given point? And of course, notice that the divergence is a number, it's a scalar, okay? Whereas the curl is a vector. What is going on? So the curl is a vector. Well, it turns out to describe rotation of a vector field, you really need a vector to do that because you need to have sort of like an axis of rotation that describes what's happening, okay? So those look like horrendous formulas, and it turns out there's some nice ways for us to see what's going on here. So we make this little fake operator called del, okay, which is created with the so-called nabla symbol. We've seen that before in the gradient, right? And so, I mean, look, even if I like all it is just partial with respect to x, comma, partial with respect to y, comma, partial with respect to z. It's almost like a little vector made from these symbols. It's weird. It's just for convenience of helping us remember this later on. Okay. By the way, if I were to, take, little f of x, y, z, and take nabla f of x, y, z, and think of f of x, y, z as like a scalar, then I would get, the partial of f with respect to x, the partial of f with respect to y, the partial of f with respect to z, right? I'll use angle brackets. It's like I sort of distributed f as a scalar into this thing. And lo and behold, that's exactly the formula for the gradient of f, yeah? So it even helps you remember that if in case you were having trouble remembering that. But del dotted with a vector field f gives you the formula, don't you see? Yeah. So del dotted with that. So this is an alternative notation, if you will, for the divergence of f. Okay. And what about the horrendous curl formula up there? Okay. Well, it's the cross product. So curl of f is given by del crossed with f, and you do the cross product, and guess what? Guess what? You get exactly the formula that was given above. Okay, right there. If you just cross del as if it were like a vector with f1, f2, f3, there's the formula right there. Okay, so you're gonna have to remember your formulas for cross products, though you've already had to do that in this class before. So hopefully that's not too big of an ask for sure. Okay. Still, the curls, granted, the curl still feels a little like it's a little bit mysterious. And we know it has something to do with rotation of a vector field, but what is going on exactly? Well, we'll talk about that here pretty soon. So again, curl of f is just del crossed with f, and divergence of f is just del dotted with f, okay, where del is this special operator right here, okay, that we just use as an aid to memory. And like I said, you can even use it to help you remember the formula for the gradient, okay? So now that we know the formula for computing the divergence in the curl, let's talk a little bit about some subtleties about the divergence. Actually, you know what? I'm going to skip this part and just move right into the curl because I already did talk about subtleties of divergence, okay? Let's talk about the curl of a vector field. I said it has something to do with rotation, okay? So here's like a big gnarly vector field sitting here. It just looks like a giant mess, don't you see? Okay, well, I can kind of twist and turn this thing and I can see, oh yeah, it looks like there's some kind of rotational stuff going on here. Okay, it looks like, oh boy, I already forgot what was happening. Yeah, so it's going kind of like, like this at certain points. Okay, that's kind of the feel that you get. But how do I describe that with any kind of real precision without us just kind of staring at this and saying, yeah, it looks like it's basically rotating kind of like this. You might have really intense rotation, and you might want to capture that somehow. So we're going to do that with this curl vector. We're going to need a vector to do it. Okay, so here's how we do it. So we're not really interested in the macroscopic circulation of fluid around circles, okay? That's not what the curl is intended to measure. We really want to measure what's happening at a point. And so what they do to illustrate this is they kind of drop a sphere into the fluid flow and they kind of anchor it at a point and they let the vector field kind of do its work as if like, those vectors were the velocity of the fluid as it kind of flowed through. And then you would watch that sphere kind of find an axis of rotation because it's anchored right at a particular point, right in the middle. and you would kind of see how that thing would rotate. And there would be a particular axis of rotation, just like there's an axis of rotation for the Earth. And that axis of rotation is what is going to represent the curl vector, okay? And you know that if you talk about vectors, you'd better be more specific. You need a direction. Well, how is the direction going to be determined? Well, by the right-hand rule, for crying out loud. Okay, so you can kind of see that it's spinning like this, yeah? And so if you take your right hand and you curl your fingers in that direction, doesn't your thumb kind of point up in this direction? Yes? Okay, it's going to point up in that direction. Okay, the axis of rotation of that sphere, it points, the spin of that thing with your right hand, your thumb dictates the direction of the curl vector, and the length of that vector is going to be longer or shorter depending on the rapidity with which that thing is rotating. So if that baby's really just whipping around like crazy, you're going to have a really long curl vector. If it's barely spinning, then you're going to have a much shorter vector there. Okay, so it's interesting. I think you can actually, can I move the sphere around? Wow, that's cool. Seems like it should change though when I do that. So I don't know, that's a little strange. I'll leave it right there. Okay. So yeah. So here's kind of the axis drawn in there, or I can kind of move this around. See that? So again, the direction of that vector is determined by the right hand rule, and the length of it is determined by the rapidity with which that sphere is actually spinning in that direction in accordance with the right hand rule. Okay. All right. So I'm going to leave it at that and go to this thing right here and try to explain why the components of the curl are what they are. I mean, remember we had this formula back here. It was like, you need to do this. Take all these differences in partials, and those form the components of the curl vector. And then we had to remember that by doing this cross product of nabla with the actual vector field itself. Well, that's crazy. Okay, why? Why is it the difference in the y partial of the third component minus the z partial of the second? What is going on? Why is that the x coordinate, for instance? Well, here they're going to give us a little bit of an explanation of that. It's pretty helpful. So again, here's the same picture we were dealing with just a minute ago. And here they say, okay, well, let's just imagine that the curl of f was given by some v1, v2, v3. Let's figure out what these things would have to be if indeed, you know, we want to have some axis of rotation for an anchored sphere at a point. Once that sphere kind of starts spinning in accordance with how the vector field is pushing it around, you know, how would I describe that with these coordinate vector, the coordinates of this vector here? Well, what they do is they isolate the z component of the curl just to try to explain that. So what they've done here is they've said, all right, not only am I going to anchor the sphere at like a center point, but I'm actually going to put it on a rod that is parallel to the z-axis. This way, it will tell me only what's happening in the z direction in accordance with this fluid flow. So again, I kind of put this thing on a string that's really taut, and I've anchored it to a particular point, and I'm only letting this thing spin along this string that happens to be anchored in the z direction. And this is only going to tell us, so first of all, you know that the z coordinate is going to be positive because this thing is spinning in accordance with the right-hand rule in this direction. So my thumb points straight up, right? So you know that this thing is going to have a positive z coordinate. But anchoring it on this rod in this way forces the situation to only take into account the z coordinate direction. Okay, so we're only concentrating on the z direction here. Okay, and then what you do is you kind of look down in the xy plane. Okay, so here's this thing, you know, it's anchored there. You look down in the xy plane and you say, okay, well, what could cause it to kind of rotate in this direction? What could cause it to rotate in this direction? Well, look, I know that I have these F1s and F2, right? Because I had capital F was equal to F1, F2, F3. What I'm doing though, I've anchored this rod, yes, and I'm only looking at the first and second component functions, the first and second component functions of this thing. Because the third component function honestly isn't really going to be doing much in this particular case. It's really just the X and the Y component functions that are causing all of this to happen up here. Yes. The Z component function isn't doing anything. It's just the X and the Y's that are kind of doing this. Okay. Now, what would cause it to rotate in that direction? Well, I would have to have a bigger amount of force over here on the right than I have over here, right? And a little amount over here, or a bigger amount down here than I have over up here, okay? I had a bigger amount on the bottom and a bigger amount on the right, that would cause this thing to rotate in a counterclockwise direction. Don't you see? If I had a bigger amount of force on the right and a bigger amount of force on the bottom, that would cause this thing to rotate in the counterclockwise direction. Well, what that means is, as I move from left to right, so think about this, what this means is, so I want to have a smaller amount of force on the left here and a smaller amount of force on the right. As I move from left to right, that means that F1, okay, which is the X coordinate function, right? So if I move from left to right, that my vectors are getting bigger, right? So the rate of change as X moves, right? Or as X moves, the rate of change, okay, for my first coordinate function here, the rate of change is positive. Okay, the rate of change of that thing is positive in the X direction. And on the other hand, what's happening here? Think about it. If this thing is big on the bottom side of this and small on the top side, then what's going on? Well, then I'm looking at sort of F2. If I move from bottom to top, F2 needs to be kind of getting smaller. I hope that kind of makes sense. F2 is getting smaller. So as Y increases just slightly, F2 needs to be getting smaller. So that means that, you know, the partial derivative of F2 with respect to Y is decreasing. Okay, so that means that the rate of change is negative for that guy, and the rate of change of F1 with respect to X, that, my friends, needs to be positive. Okay, so overall, what would have to happen? Well, I would need the partial derivative of F1 with respect to X minus the partial derivative of F2 with respect to Y. So like the negative sign would turn that negative rate of change of the second component with respect to Y would change it to positive, right? That, remember, I want the Z component to be positive, yes, so that I get this right-hand rule rotation. This would be positive on the whole, yes? So notice that I end up looking at this quantity right here. This quantity right here is what I end up looking at, which interestingly is exactly, so hang on a second, F2, is it F2? So F2, what's F2 doing here? So oh, right. So F2 is actually describing these things. I think I have these things flipped around here for whatever reason. Okay, so F2 is the Y component. Yes, right, because these things are going up like this. Oops, I'm sorry, guys. F2 is going up like this. So actually, I should have these two things flipped around. Yeah, F2, F1. So it should be F2, and this should be F1. Sorry about that. I apologize. Because F2 is kind of pointing up F1. F1 is describing change in the X direction. Yes, change in the X direction, which is why these arrows are pointing like this, okay? But what you're doing is you're watching how those arrows move as Y changes, okay? Which is a little bit confusing, okay? But that's why you end up looking at this difference, F2 of X minus, or the partial derivative of F2 with respect to X minus the partial derivative of F1 with respect to Y. If that's positive, you're gonna have a positive Z component there, okay? And the bigger that is, the more rapid the movement is around that rotational, rotation around that axis, okay? So I'm going to go back over to here now and go down here. Okay, so I'll come back and talk about some of these things like conservative and a potential function later on. But what I mainly wanted to do was just do a couple of computations here in closing. And we'll talk about irrotational and things like that. But here's the formula for the curl. It has the things like the del crossed with F, for instance, and del dotted with F. Okay, but let's actually do some computations here. Okay, so we'll come back and talk about what conservative means exactly. That's something that we'll talk about later on. But here's this vector field right here. Okay. Y e to the z, x e to the z, and e to the z. Okay, how do I compute the curl? Well, it's del, right? So here's del right here, del crossed with the vector field, which is the next thing down here, right? And you remember how to do this, right? You cross out the x coordinate, and then you go this times this, minus this times this. So it's going to be the partial derivative of e to the z with respect to y, which is 0, minus the partial derivative of z of x e to the z, which is just minus x e to the z, etc. Then you go through and you do that. And look, I mean, this is the only one that's kind of tricky is you cross out the middle coordinates here, and you have to do these things kind of in reverse. So you do the partial derivative of z of y e to the z, which is just y e to the z, minus the partial derivative with respect to x of this, which is why it says minus 0 right here. Okay, and then the last one, you go this times this, partial derivative with respect to x of that, which is just e to the z, minus the partial derivative with respect to y of y e to the z, which is e to the z, and you get 0. Okay, and so here is the curl of this thing. And notice I'm saying no here, that's in answer to the question whether this thing is conservative. Conservative basically means that the thing is irrotational, if you will, irrotational, that there's no rotational tendencies whatsoever, but we'll come back and visit that a little bit later on, okay? So hopefully that's been a little bit helpful. We will come back and we'll visit some of these things and talk about some particular properties of the curl and divergence that are going to be important for us. For now, just knowing what the curl and divergence are, I'm not necessarily concerned with you, having to be able to explain every single aspect of what's like why this formula is what it is, for instance, but just having a good understanding of what the curl is telling us. It's telling us sort of a tendency for the vector field to rotate at certain points, and the divergence is telling us whether you have sinks or sources at given points. And we even have formulas to compute these things as well. And there's going to be a couple of other things we're going to want to know in relationship to what the curl is and what the divergence is. Then we're going to start utilizing this in various ways, and we will see some very interesting results that will perhaps be surprising and will end up being utilized with fair frequency later on in your careers, I'm sure. But that's all for now. Thanks for watching.